Hello, my name is Jay Campanell. I'm a student at the University of Southern California, and today I'll be presenting using AI to forecast child malnutrition in Kenya. This is a joint project with the USC Institute on Inequalities in Global Health, Microsoft AI for Social Good, the USC Center for AI and Society, are now partners in Kenya, Amref, and the Kenyan Ministry of Health. So, what is the problem we're trying to tackle? Well, in Kenya, for children under 5 years old, there's the leading cause of mortality and morbidity is malnutrition. And the Kenyan Ministry of Health found that roughly 5% of all children in Kenya face some sort of acute malnutrition, a level considered a public health concern. So, what is being used now to tackle this? Well, a lot of it relies on ground operator knowledge of historical trends. So, there's not much data being integrated into decision-making processes, and if it is, there's no automation or statistical modeling, making it difficult to predict where there might be issues, where there might be more or less malnutrition, and placing a burden on those who have to make those predictions. So, in addition to easing the burden, there are some other issues with this purely historical trend and using purely historical data. There's no clear seasonality. If we look at the two sub-counties listed here below, Tiaty East, Mandera West, we can see that there's no cyclical pattern that always reoccurs. There's also non-linear patterns, and there's variance spatially. Mandera West and Tiaty East are two sub-counties on opposite sides of the country, meaning there's some spatial element going on as well. So we had three objectives with this project. The first one is to develop a spatio-temporal model using clinical data, enhance that model using external data sources such as remote sensing imagery, and then three, create a set of sustainable tools that can allow for easy integration into daily workflows to make sure these models actually get used. So we had two main data sources for this project. We had our clinical data from DHIS2 from the Kenyan Ministry of Health, which collects data from around 15,000 clinics around the country on a monthly basis. Then we also have gross primary production, or GPP, which is collected weekly, and we use to aggregate to the monthly level from NASA's MODIS satellite. And this is a measure of crop productivity and photosynthesis. So our clinical data, like I mentioned, 15,000 clinics, and it reports clinical indicators as well as our malnutrition outcome indicator, which is our mid-upper arm circumference, or MUOC, which is reported as a normal level, moderate, or severe. So if the circumference, which is a measure for malnutrition, is moderate, normal, or severe, it gets reported as a count. So using these counts, we're able to derive and turn those into our classification, which is that integrated food security phase classification. We found acute malnutrition to be moderate plus severe cases, and then we standardized that by a rate to convert it to a scale that you can see here. So for our GPP data, we kind of use this, and like people may be wondering, why do you use photosynthesis data? Well, there seems to be an inverse relationship between gross primary production and malnutrition, meaning it can be a good indicator, especially if we don't have clinical data to feed into our model. So how did we actually model this? Well, we split our data temporally from training, testing, and external validation data to forecast on, and then we used our baseline model of a window average model, which simulates what's currently being used, which is you take the past few months, average the values, and then you figure out what is the malnutrition based on that average. So if that average is something, that's going to be your forecasted value. Our statistical models, on the other hand, we use a gradient boosting model, which I'll be focusing on today, which is an ensemble technique which sequentially builds decision trees and learns from each one, and this is really great at capturing non-linear relationships. So we created a pretty simple workflow where we take all of these data sources, we aggregate them to the traditional sub-county level, convert those absolute numbers to rates, map it to our IPC scale, create the data fusion, and then we put it through our model training and testing and create our new forecasts. And one reason we have to have a pretty simple workflow is due to computational constraints that we have in Kenya. So what did we actually find and what did we get? So we developed three variations of our XGBoost model depending on different data availability. So we have one that uses just satellite data, one that uses just clinical data, and then one that combines all of our sources. And we created 3 time horizons, 1, 3, and 6 months. We found that across all of our time horizons, there's not much data degradation, and our best performing model obviously includes all of our data, but also good to note that our window average and satellite models do match pretty well, so even if we don't have clinical data, we can still use that. Similar things for our stratifying across each IPC range. We can find that the mid-range struggles the most, while in the highest range, we get pretty consistent accuracy. So what are our outcomes, next steps, results? What are we doing? We're actually developed a dashboard that can be used to figure out where there may be issues, as well as creating a set of forecasting tools to be able to help the people in Kenya and our partners to be able to make their own forecasts. And so what did we prove? We proved that it's possible to predict child malnutrition with a spatiotemporal machine learning model. We didn't use any new data, no data collection, and we created a flexible framework that can be used for early forecasting. So thank you so much for listening. You can contact me at the email, and thank you again to all of our partners.